In an electrical system design involving a transfer switch and a generator backup, several factors must be considered regarding grounding and overcurrent protection. The core of the issue is whether to move the neutral ground bond to the transfer switch and whether a 4000 amp circuit breaker is necessary at the transfer switch's normal feed. Arguments exist on both sides. Considering the arguments for moving the bond and installing the 4000 amp circuit breaker, firstly, safety is paramount. The 4000 amp circuit breaker provides overcurrent protection for the transfer switch, protecting both the switch and the neutral ground bond from potential damage in the event of a fault. Secondly, code compliance is essential. The National Electrical Code, commonly referred to as NEC, mandates a disconnecting means at the first point of service entrance. In the described scenario, the transfer switch effectively becomes the initial disconnecting means for the portion of the main switchboard that it feeds. Therefore, it must incorporate a disconnecting means rated for the full load current of the service, in this case, 4000 amps. Thirdly, maintaining neutral grounding integrity is vital. By disconnecting the bond in the main switchboard, also known as MSB, and relocating it to the transfer switch, the neutral and grounding systems remain intact, adhering to NEC requirements. Now, considering the arguments against moving the bond or installing the 4000 amp circuit breaker, firstly, simplicity is a significant factor. Retaining the bond in the MSB simplifies the electrical system and minimizes the potential for errors during installation or subsequent maintenance procedures. Secondly, cost considerations are important. Installing a 4000 amp circuit breaker and extending the grounding electrode conductor, commonly referred to as GC, can substantially increase the project's overall cost. Thirdly, some argue that redundancy exists. Certain engineers believe the 4000 amp circuit breaker is unnecessary because the transformers already offer overcurrent protection. Despite these opposing arguments, it is recommended to follow certain steps. Firstly, consult with a qualified electrical engineer. Their expertise provides guidance based on specific project details and adherence to local code requirements. Secondly, carefully consider the safety advantages of relocating the bond and installing the circuit breaker. While it may increase costs, it significantly enhances the overall safety and reliability of the electrical system. Thirdly, meticulous documentation is crucial. Clearly explain the rationale behind a chosen design in the project documentation. Let's delve deeper into the technical aspects of grounding and overcurrent protection in electrical systems to fully grasp the importance of these decisions. Grounding systems are designed to provide a low impedance path for fault currents to return to the source, enabling overcurrent protective devices to operate and clear the fault quickly. This minimizes the risk of electrical shock and equipment damage. The neutral ground bond is a critical connection that ties the neutral conductor to the grounding system, creating a reference point for voltage and facilitating the flow of fault current. The NEC provides detailed guidelines for grounding and bonding in Article 250. It specifies the requirements for grounding electrode systems, grounding conductors, and bonding methods to ensure a safe and effective grounding system. Overcurrent protection is another essential aspect of electrical safety. Circuit breakers and fuses are designed to interrupt the flow of current when it exceeds a predetermined level, protecting equipment and personnel from damage and injury. The selection of overcurrent protective devices must be based on the ampacity of the conductors they protect and the interrupting rating required for the specific application. The NEC provides guidelines for overcurrent protection in Article 240, including requirements for the type and size of overcurrent protective devices, as well as their location in the electrical system. The transfer switch plays a vital role in providing backup power to critical loads during a power outage. It automatically or manually switches the load from the normal power source to the generator. Transfer switches must be properly rated for the voltage, current, and interrupting capacity required for the application. They must also be equipped with appropriate overcurrent protection and grounding connections to ensure safe and reliable operation. When a transfer switch is installed at the service entrance, it becomes the first point of disconnect for the building's electrical system. In this case, the NEC requires a service disconnect rated for the full load current of the service. This disconnect must be readily accessible and capable of interrupting the flow of current to the entire building. The 4000 amp circuit breaker being considered for installation at the transfer switch would serve as the service disconnect in this scenario. The NEC also requires that the neutral ground bond be located at the service entrance. This means that if the transfer switch is installed at the service entrance, the neutral ground bond must be located at the transfer switch. Disconnecting the bond in the MSB and moving it to the transfer switch ensures compliance with this requirement. The grounding electrode conductor, also known as GC, connects the grounding system to the earth. It provides a path for fault current to flow to the earth, helping to stabilize the voltage and reduce the risk of electrical shock. The size of the GEC is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. Extending the GEC from the transfer switch to the grounding bar in the MSB ensures that the grounding system is properly connected to the earth. In the specific scenario described, the owner's engineer has concerns about the 4000 amp circuit breaker and the relocation of the neutral ground bond. They argue that the circuit breaker is redundant because the transformers already provide overcurrent protection. However, it's important to understand that the transformer's overcurrent protection is designed to protect the transformers themselves, not necessarily the downstream equipment and conductors. The 4000 amp circuit breaker provides additional overcurrent protection for the transfer switch and the downstream electrical system. It also serves as the service disconnect as required by the NEC. The owner's engineer also argues that keeping the bond in the MSB simplifies the electrical system and reduces the risk of errors during installation or maintenance. While this may be true to some extent, it's important to consider the potential safety implications of not relocating the bond. If the bond remains in the MSB, the neutral and grounding systems may not be properly connected, which could increase the risk of electrical shock. Ultimately, the decision of whether to move the bond and install the 4000 amp circuit breaker should be based on a thorough evaluation of the specific circumstances of the project and the applicable code requirements. It's important to consult with a qualified electrical engineer to ensure that the electrical system is designed and installed in accordance with all applicable codes and standards. In this case, if the owner's engineer has concerns about the 4000 amp circuit breaker, they should provide clear justification and alternative solutions that comply with the NEC and ensure safety. They should also be prepared to document their decision-making process and explain the rationale behind their chosen design. Moving the neutral ground bond to the transfer switch offers a more comprehensive approach to safety and code compliance, particularly when the transfer switch serves as the service entrance. While cost and simplicity are valid considerations, they should not outweigh the potential risks associated with inadequate grounding and overcurrent protection. The decision should be based on a holistic evaluation of the electrical system, considering both the technical requirements and the potential safety implications. For instance, NEC Section 230.95c discusses ground fault protection of equipment. Ground fault protection of equipment shall not be required for services of more than 150 volts to ground but not exceeding 1000 volts phase-to-phase on systems used exclusively to supply industrial processes or activities, where the continuation of such processes or activities is necessary for safe shutdown of plant or equipment. NEC Section 250.24 covers the grounding of service-supplied alternating current systems. System grounding connections must be made at any single point on the supply side of the service disconnecting means. This single point can be the neutral point, the grounding electrode conductor connection, or the supply side of the service disconnecting means. This clarifies the location for the neutral ground bond. Additionally, NEC Section 250.28 discusses bonding jumpers. Bonding jumpers are used to connect the equipment grounding conductors and the grounded conductor at the service equipment. These jumpers must be sized according to NEC Table 250.102. For example, if the service entrance conductors are 500 kcmil copper, the bonding jumper must be at least 1/0 AWG copper. NEC Section 310.16 provides the ampacity of insulated conductors. The ampacity of a 500 kc milk copper conductor with THHN insulation is 380 amps when installed in a raceway or cable. This information is used to determine the appropriate size of overcurrent protective devices. NEC Article 408 covers switchboards and panel boards. Switchboards and panel boards must be marked with the voltage, current rating, and interrupting rating. They must also be installed in a readily accessible location. NEC Section 445.13 discusses overcurrent protection for generators. Generators must be protected from overcurrent by a circuit breaker or fuse. The overcurrent protective device must be sized no larger than 115% of the generator's rated current. NEC Section 700.12 covers wiring of emergency systems. Wiring for emergency systems must be kept entirely independent of all other wiring and equipment and must not enter the same raceway, cable, box, or cabinet with other wiring. NEC Section 701.11 covers wiring of legally required standby systems. Wiring for legally required standby systems must be kept entirely independent of all other wiring and equipment and must not enter the same raceway, cable, box, or cabinet with other wiring. NEC Section 702.11 covers wiring of optional standby systems. Wiring for optional standby systems may occupy the same raceways, cables, boxes, and cabinets as other wiring. NEC Section 705.12 covers interconnected electric power production sources. Interconnected electric power production sources must be provided with a disconnecting means that is readily accessible and capable of disconnecting all sources of power from the premises wiring. Therefore, the decision of whether to relocate the neutral ground bond to the transfer switch and install a 4000 amp circuit breaker requires careful consideration of safety, code compliance, cost, and simplicity. Consulting with a qualified electrical engineer is essential to ensure that the electrical system is designed and installed in accordance with all applicable codes and standards. The engineer can assess the specific circumstances of the project and provide guidance on the best course of action. For example, if the owner's engineer argues that the transformers already provide adequate overcurrent protection, the electrical engineer can evaluate the transformer protection scheme and determine whether it is sufficient to protect the transfer switch and downstream equipment. If the owner's engineer argues that keeping the bond in the MSB simplifies the electrical system and reduces the risk of errors, the electrical engineer can evaluate the grounding system and determine whether it meets the requirements of the NEC. The electrical engineer can also provide alternative solutions that address the owner's concerns while still ensuring safety and code compliance. In addition to the technical considerations, it is also important to consider the legal and liability implications of the decision. If the electrical system is not designed and installed in accordance with all applicable codes and standards, the owner may be liable for any damages or injuries that result from an electrical fault. Therefore, it is essential to document the decision-making process and explain the rationale behind the chosen design. This documentation can be used to demonstrate that the owner took reasonable steps to ensure the safety of the electrical system. In summary, the decision of whether to relocate the neutral ground bond to the transfer switch and install a 4000 amp circuit breaker is a complex one that requires careful consideration of a variety of factors. Consulting with a qualified electrical engineer is essential to ensure that the electrical system is designed and installed in accordance with all applicable codes and standards and that the safety of the electrical system is not compromised. A coordinated approach between the owner's engineer, and the electrical engineer is critical to ensure a safe and reliable electrical system. The primary objective is to protect people and property from electrical hazards, while also ensuring the continuity of power to critical loads. Therefore, it is recommended to follow the electrical engineer's guidance, as they are trained and experienced in designing and installing electrical systems that meet all applicable codes and standards. Finally, it is important to remember that electrical codes and standards are constantly evolving. Therefore, it is essential to stay up to date on the latest requirements and to consult with a qualified electrical engineer whenever making changes to an electrical system. Careful consideration of all factors and a commitment to safety and code compliance will help to ensure a safe and reliable electrical system for years to come.